So, hello everyone. So welcome to this week AI UCI workshop. So it's week 9. The time is pretty fast, but anyway. So our topic for this week is multitask learning and meta learning. So before we start, it's definitely we want to talk about the problem that can be solved by multitask learning and meta learning. I think most of you guys probably, when you play around with neural network or training some neural network to solve some tasks, you'll definitely see cases where you don't have enough training samples, right? Or the data set is not good, it's really skewed. So what multitask learning and meta learning is some way that you can try to solve those problems. It's definitely not the only way. You can definitely, for example, generate some synthetic data or those kind of things. But it's good to know to more ways. So first of all, let's talk about the difference between multitask learning and meta learning. Although I put them into the same topic as workshop, but they do have some little difference. So for multitask learning, is we want to learn all tasks more quickly together rather than learn them independently. I will show you an example in the next slide, I think. And well, for metadata, it's given data experience from previous tasks. We want to learn a new task more quickly and more accurately. Take a look at this for like probably 10 seconds, try to understand it. It's fine if you don't understand 100%, but try to get a feel of this because, if any question, definitely just raise your hands or type in the chat so I can answer the question. Yeah. So this is an example of multitask learning. So what multitask learning is you want to learn multiple tasks at the same time. So above is one of the potential architecture that people use in multitask learning. You first start with a bunch of shear layers, and then you will have a task-specific layers. And below here is the more like real-world scenarios. Say, for example, you give an input image, then you do, besides the semantic task segmentation, instant task segmentation, and also depth task segmentation. And then you basically combine the loss together. So why is this work? So I think because in this example, right, most likely they will use convolutional neural network to do those kind of things. So if you know what convolutional neural network is, you will know that there's like multiple layers which in a CNN network. And in the beginning layer, the convolution, the kernel, are learned to do some really basic low-level tasks. For example, edge detection, for example, reducing some noise. And since those three tasks are so similar, if we train those tasks separately, do you think they will have really different weights, or do you think they will have similar? They'll have similar weight, right? So if that's the case, why don't we combine and basically make them into shear layers? Another good thing about this is imagine, okay, there's like 3 different tasks, right? On each task, we have like X data point, and X can be a relatively small number. If we can basically combine them together, in the shear layer, you will actually receive 3 times X the data point number. So you'll get more data from it to do better, training and prediction. And of course, if tasks are like less, similar to each other, you can have less shear layers. And if the tasks are more similar to each other, you can have more shear layers and less task-specific layers. And this terminology for this is called like positive transfer and the negative transfer. Positive transfer is basically when you train multiple tasks, you reach a high accuracy compared to when you're training only one task at a time. And negative transfer is basically the vice versa. So the reason is most likely because of that. Anyone has any questions right now? Or do you want to rephrase it again? All good? Yeah, so that is multitask learning. Really straightforward. So next one is meta learning. Meta learning, the objective of meta learning is to learn to learn. I think this is probably going to sound a little confusing for a lot of people, but what essentially okay, I'll take a step back and tell the reason why we want to try meta learning. So what's the main difference between human and the AI? Do you know what's the main difference?
Generalized.
Yes, definitely. See, like if you especially doing the reinforcement learning area, you will find out that like a lot of time, even like for example, AlphaGo, AlphaZero, they are like they in certain game setting they can surpass humans, best human player. But at the same time, if you deploy the same agent into other game environments, you'll reach terrible accuracy, or sometimes it's not even trainable at all. And if we want to train them again, we have to basically train them from scratch. And each time if you want to train them from scratch, you know that it at least takes hours or even days of training and millions of trajectory for a game. Like this is one of the examples, like people always say that why reinforcement is really hard. It's called multi-small revenge. It's basically, I think you start with the character, you have to reach the goal, and there's a lot of obstacles. And for human, I think most of us, if we want to play this game, although we don't know what this game is about right now, but if we actually play this game, in 30 or 40 tries, we will have a basic idea of how to, basically, pass the game, right? But for machine learning, for reinforcement learning, they cannot do that. We gotta specifically inject a lot of domain knowledge and basically let them train a lot of time in order to reach similar human performance. And I have a hypothesis for this. The reason we can do this because we have something called common sense. We know that for example, if you want to learn a new math formula, right? A lot of time we want to put some logic behind it. We don't just use millions of training examples to memorize the pattern. We don't do that. Clear? And I think someone else, when I was learning this kind of concept, they did a really interesting experiment. I think they either it's just for this game or some other games, they basically change the pixel around, right? Because for us, when we play the game, we also see this screen, right? They change the pixel around. For example, for the blue letter, they may change to something else, the other shape, other kind of shape, or other colors, such that we as a human cannot use common sense to basically play the game. And as expected, human cannot play the game at all, even with 100 or 200 tries. So that's why I think common sense is pretty important. And at least in my opinion, meta learning's job is try to help the AI to develop some type of common sense in order to generalize tasks well, so it's easier to learn, faster to learn. And in meta learning, there's basically 3 types of algorithm. The first one is optimization based, the second one is matrix based, and the third one is model based. And then we'll go over all this in the future slide. So I guess just want to make you guys understand what I'm saying. Imagine this task, there's 2 images from the animal called armadillo and pangolin. I don't think anyone knows what those animal is, right? Most likely. And I'm just here to ask, what is this animal? Is this armadillo or pangolin? Give you 10 seconds. Right? Anyone here think this is armadillo? And everyone probably thinks this, right? Yeah, the reason we if you do the same thing to the machine learning algorithm, it's not gonna learn anything, right? Because 2 images is way too little for machine learning to learn anything useful. The reason we can do this is because besides we can separate different images into different classes, we also know how to tell the difference between images. And we definitely know that this image are pretty different from this image, especially the shape of the animals, right? So, we want to tell machine to learn those kind of things. And meta learning, okay, after talking about the basic method of meta learning and some basic concept of meta learning, let's talk about the detail of meta learning. So in the meta learning algorithm, when we actually train the task, usually consists of a meta training data set and a meta testing data set. It's definitely different compared to supervised learning. So I'll probably stop for 10 seconds and let you guys try to take a look at it. In each meta train and meta test, they are both a smaller data train sample and a smaller testing data sample. Think about this, it's going to be a little confusing in the beginning. Just some more. Yeah, try to take a look at it. So it's definitely different compared to the traditional supervised learning you see, right? Where there's only one training, one testing, and sometimes it's a validation and testing. The reason we want to do this is we want in the meta training, right? In meta training algorithm, we care about how well the model can generalize, how easy a model can use to learn a new task. So that's the reason why we use this method to test the thing. In the meta training data set, we're going to first train a meta algorithm, and based on the metadata algorithm, we're going to learn a task-specific algorithm. And the task-specific algorithm objective is to basically optimize the accuracy between this small data train and data test. But in the metadata algorithm, the job of metadata algorithm is to help the task-specific algorithm to reach as high as accuracy as possible. Maybe a little confusing. Do you want me to rephrase this again? Think about it as when we're doing this kind of training, we're going to first train a meta algorithm. And then we're going to train a task-specific algorithm. Just imagine this case. The task-specific algorithm, the goal is to basically try to reach as high accuracy as possible to predict, for example, is this a dog or is this a piano? And the metadata algorithm is basically, the goal of meta algorithm is to help task algorithm to make prediction. Because imagine if you only have a convolutional network, only have this 5 image and this 2 image, it will not train well at all. Do you agree? So that's why we want to train a meta algorithm to help them to basically increase the accuracy. I think this is the most important point about meta learning. I hope you guys can understand. All good? Yep. So I think a lot of time, especially if you're reading some paper or few-shot meta learning, you will see a few-shot learning examples. A lot of time also K-way N-shot learning. This is just a terminology. K-way is basically represent how many different classes you have. N-shot is how many examples you have. Say for example, in this case, there's 5 different classes in a testing set, and each classes only have 1 example. So in this way, it's 5-way one-shot learning. And if we go back to supervised learning case, right? Imagine ImageNet. Most likely is 20-way, 1,000-shot learning, something like that. But you know. So this is a terminology. If you're interested, definitely have to understand this part. Everyone good so far? Okay. So now let's talk about the actual algorithm. The first one is optimization based. I think, in my opinion, this is the most general meta learning algorithm, and the name is basically model agnostic meta learning. The reason it's really general and it's powerful is it doesn't care about what kind of task the meta learning algorithm is being trained on. It's kind of similar to transfer learning. However, in transfer learning, we usually transfer from a good accuracy model. However, in meta learning, we don't care about the original model performance at all, right? I think most of you guys probably know transfer learning is, right? You take, for example, BGG16, like in computer vision examples, and you basically put the same model into the task you want to train on. And usually the task you train on has really little examples. And usually you can reach really good accuracy by doing fine tuning. So, it's kind of similar idea, but the difference is in the line 3. And that is the goal of optimization learning. And this is an example over here. I guess there's no marker over here, right? You have markers? Probably not. I have marker. Okay, thank you. Thank you very much. Wonder, can you see me? I don't think you see you, right? I see the bottom. Wait, where? Oh, yeah. Yeah. Switch to. Okay, I'll try over here. So every single time, right? I think most of you guys, if you train machine learning model, usually you will first randomize sample point. Imagine it's over here. And you will first, take a lot of epochs. You will basically, the loss will gradually go down, and then basically stabilize. Basically converge. And imagine the way the converge points over here, the model converge points over here, we start from here. Those are the steps, the gradient step we have to take in order to reach convergence, right? And imagine if we initialize the model weight over here. The amount of time we need to do convergence is going to be much smaller. So that's basically the goal of optimization-based meta learning is try to find a point such that you can take as little step as possible to basically reach good accuracy. And of course, if there's only one task, the best place is getting initialized like this, right? But this since we want to be as general as possible, then the goal of optimization based learning is to find the point to initialize the weight such that for all tasks, in that domain, you can basically generalize as fast as possible. Understand? And I think this image probably can show this fine. And data 1, data 2, data 3 are basically the most optimal weight for the task. And the best place to initialize the weight should be just this point. So we basically gradually, find this point over here. And of course, some people may ask, how do we actually achieve that, right? And especially since the way we try to reach the conversion is based on gradients, right? So in a really simple term, we just take the gradient of gradient. And the real math behind it, the proof is a little difficult, but if you're interested, I will share the link where I get the information. Just like a professor from Stanford, she's giving me she's basically publishing some free class on YouTube. And in her class, she shows the pretty good proofs of how to actually achieve this and the math behind it. But basically, if you're interested, just remember, we take the gradient of the gradient. And then we can basically do this. And the second one is matrix space. This approach basically involves learning a matrix space in which learning is particularly efficient. So remember in the beginning, I talked about the reason we can, let's go back here, can be distinguish this one as a pangolin instead of armadillo. It's because we can tell the difference between images, right? Not just, remember the pattern of each class and the separately. So the goal of matrix learning is kind of like that. You kind of want to encode, given an image, right? You kind of want to encode the image from the same class as close as possible in the feature space. Well, the image from different class be as far as possible. So it's kind of like k-nearest neighbor approach. So if you guys know about that. So you basically encode, like given a random image, you'll basically encode here, imagine C2, and use that, we can basically classify if this is a C2 or C1. Clear? Any questions? Few shots, zero shot. And the third one is model-based. It's a black box approach. It's basically encode new information. It's try to encode new information fast and thus to adapt to new tasks after only a few examples. The reason it's called black box approach because a lot of time it basically take so instead of having all those like things, you basically have a model that designed specifically to do those kind of tasks. For example, in this case, imagine you have a model. There will be some fast weight layer that basically are used to basically update rapidly just for that specific task, and some slow weight layer that have been trained by the meta learning algorithm that help the task specific model to do prediction. This one is definitely a little complicated, so I'm not going to too detail in this. How is the speed of the weight layers? Sorry, what do you mean by how is the speed of the weight layer implemented? How is the weight layers implemented? Are you saying how do we initialize the weight of a model? Or
oh, I was just confused with the fast and the slow. What's the difference between those two
but
layers?
if you ask about like initialize the weight of the model, most of the time we just randomize it. I think we have some specific way to try to basically initialize as uniform as possible, such that we can converge faster. But if that's what you ask, yeah.
Okay, got it. Yeah. Thanks.
Yeah, if you have more questions, you can just type in the chat. I will take a look at later. And now I think we're going to show examples of matrix-based meta learning algorithm. So if everyone can open up their if everyone can basically open their laptop or like something if you want, and open up this Jupyter notebook.
It's on Discord.
Everyone ready? Oh, shoot, can't wait. I'll probably wait for a little bit more. Yeah, for this one, make sure you turn the GPU on, what's the thing called? GPU on, because the model is pretty big and it will take a while to run. Yeah, you turn the GPU on by go to the runtime, change runtime type. And you can just change the GPU. Okay. And make sure to turn it off after.
Where is the tutorial? Well, where's the link?
I think it's on the Discord. Yeah. When you open it up, make sure you change the GPU, and after you finish, turn it back to none, because you will still count your time even if you didn't run anything. Yeah. Ready? Okay.
Get started.
Okay, so basically the goal of this is to demonstrate a few-shot learning. So the first block is import all those model. I think I shouldn't say too much about it. The second thing is the data set we're using this time is called Omniglot. Omniglot is basically a data set that has many different characters. It's kind of like MNIST. Besides, it's for different kind of characters and a lot of different classes. But for each of the classes and each of the characters, there's only like 10 examples or something, such that it's not like MNIST that we can just train neural network to do prediction on top of it. We have to utilize meta learning or sometimes transfer learning in order to do those kind of tasks. So we basically download data set and download it. And then we basically create an Omniglot data set. So the thing we're doing is a thing called Siamese network. I didn't include image about it. The basic Siamese network is the given two image, you will run the same network. Same convolutional neural network and get a feature space. And if the two images are from the same class, the feature space need to be as close as possible to each other. But at the same time, if they're from different class, we want them have to be as far away from each other as possible. And given this Siamese network, we're able to solve the few-shot learning, which I will demonstrate later. So let's go back. So what the data set over here is basically initialize the Omniglot data set. And for this one, we want to have a set size, how many times we want to run the algorithm. And if I will basically have this thing to basically either choose to have images from the same size, from the same class, or from different class. As you can see over here, and then we return them. And we also add a label if it's 0 if they're from different class, and 1 if they're from the same class. So that's really simple. Anyone has a question right now? That's what it does. It's basically just take a random image and take two images randomly. And if given some situation, like 50% of the time, you are from the same class, 50% of the time we're from different classes. And we'll have a label to do that. And we basically set the root of the thing because all the data has been downloaded in here. So we basically initialize all the things, all the categories. And this is the way we basically evaluate our algorithm, right? Because we want to do n-way one-shot learning. So remember I said, okay, n-way just means how many class. Here. Yeah, basically n-way means how many class we have. And the shot is how many examples we want to provide in the support set. So this basically does that. You know, you can pass in how many ways you want, and then you will basically do that. If you're interested, definitely take a look at the code. It shouldn't be too difficult to understand. And then we basically create a data set of 10,000. You can do as many as you want. and basically split, trim, and test. Very simple. And for the testing, there's like test size, and you can have different ways of test. If you have 10, the runtime definitely be slower. I choose 5 this time. We can play around with it after the workshop and see how algorithm performs. And this is an example if they're from the same class, you know. Although their shape is different, but you know they have the same kind of shape. No. And this is if they are from different classes. It's pretty clear, right? They're from different classes, they're different shapes. All clear? So, and now we just create a model. So this is like you can have different implementation of Siamese network, but the idea is just, you know, if given two image, they're passing the same convolutional neural network. If they are the same from the same class, they will want to be, the feature space want to be as close to each other as possible. And if they are from different classes, you want them, the feature space to be as far as possible. And how we measure the difference is basically like this. We basically use the absolute between the x1 and x2. As you can see, they basically pass to the same convolution layers. Okay. And then we basically do the initialize everything. And you should get probably 37 million training parameters. Yeah. Yeah, it's a lot. So make sure you have GPU turned on, and then we can also take the checkpoint. And then the training function, you know, it is a typical loss about, you know, also guys probably should see this since this is just a really typical PyTorch. And then we just evaluate them. And now we just train them. Yeah, and you will take a while to run, but you can definitely pause this after a while because it saved the weight every epoch if it improve the accuracy. So, but after you run this, you can test the thing and you can print the loss. So that's like a really simple demo. So if you have any question about the code, you can definitely just ask me right now. I can try my best to help you understand. Anyone have any questions? Yeah, it'll probably be a while since, you know, each epoch takes 1 minute or so. So yeah, I will probably pause it in epoch 3. You guys can let it keep running. You can have more epochs if you want. Yeah. Yeah, so I think is anything else. Yeah, so basically those are the two sources that I highly suggest if you're interested in meta learning. This one is the YouTube playlist I mentioned above a while ago. I think I will send them. I'll post it on Discord. And
Excuse me. I'm kind of just auditing this. So I was wondering, where is that Jupyter notebook available again?
oh, it's Google Colab. It's just a website. Google have this.
I know Google Colab, but what I mean is all this code you have, the notebook itself, is that available?
It's on our Discord.
Each one of this code.
We will publish this later. Yeah.
Oh,
Also, this is code from one of the blog posts I found, so I will definitely post the source as well. Yeah, I just make some simple modification. Yeah, but yeah, I'll post everything after the workshop. So now I will just try to send this to source to you guys, so that you guys, if you guys are interested, take a look at it. It's not. I don't know why this doesn't work, but yeah, I think I'm gonna pause it over here. You guys should definitely let it keep run for a while. But basically, as you can see, this is the accuracy about the N way, 85%. And it's 81% given 100 testing image. You can definitely try with more classes, like more way, and more testing samples. And you can all set them at here, number of different classes. So you can definitely play around with it and see how powerful you can get. What? Can I find computer? Yeah. Any question? Okay, so I guess I hope this workshop can help you to give a brief understanding of what meta learning is. And in the future, if you're interested, take a look at the source I'm about to send. I think I'm going to do like this. I'm going to put it here. I think you guys refresh the notebook, maybe you can see this thing. Yeah. All right. I'm going to stop running. Oh, yeah, sure.
I have a question about the Chinese network. Was it I did kind of like define a model and call it twice to share weights. And in here, in the Python version, be like just passing to the inputs with doing the same thing.
Yeah, because like what do you mean by call it twice and
Yeah.
share it?
When you have the like net plus net.
Yeah.
I just create a model and then I pass like passing the input twice and then calculate it outside, calculate.
Yeah, I think it's different. That you can have different implementation of the Siamese network. And for Python, since we're basically having a computational graph, as long as they are basically from the same, they basically use the same way to basically process x1 and x2. The computational graph will basically make sure that the weight is the same, right? Because in the end, we initialize the weight in here, So as long as in the forward function, we call it, you'll be fine. Yeah, you can take a look at the code, but play around with it. Yeah. And I think you guys should also see the link, right? Since if you do a refresh, yeah. It's definitely, I think, in my opinion, one of the hardest topics to understand, especially around the math involved. But also this area of definitely a lot of people doing research in this area because in my opinion, if you can solve this problem, you can actually create the general AI, Thank you very much. And I'll probably stay here for a little while. It's only 41. So yeah. If anything you want to share or question to ask, then definitely try to ask me.
The club meets twice a week. The club meets twice a week.
Once per week.
Yeah. Oh. Yeah, we technically have paper meetings on every Wednesday. If you want to vote. But I think we're lost with it this one.
Good morning.
It's on Zoom.
And
Andy. How do you check? I guess I'm no longer president. He goes next president. I'm retired.
but yeah,
So what's Wednesday's topic?
For the Zoom meeting. It was like weight poisoning or something like that.
Is it transfer learning?
Yeah. No, it was like how to. Wasn't the email?
Neural networks can be manipulated by pre-trained weights during transfer.
Yeah. So it was the weight poisoning paper.
I'll
Yeah, you can turn it off. But thanks for showing up.